All right, it's 4 o'clock, so we'll get started. Good afternoon, everyone. I just want to introduce myself. I'm Jennifer Rooks, Communications Coordinator on behalf of the Department of Aerospace Engineering. And I'd like to welcome and thank you all for joining us this afternoon for the first University of Maryland Distinguished Scholar Teacher Lecture of the school year with Dr. Derek Paley. Before we get started, I just wanted to make a couple of brief announcements. This afternoon's event will be recorded. And we will have that available not too long after today's event concludes, as well as we would like to let you know that we will have a brief question and answer period at the end of today's event. If you would like to ask questions to today's presenters, please use the Q&A feature. You can find that at the bottom of your Zoom feature or your Zoom screen, apologies. So please do put your questions in there. And if we choose your question, we'll call on you. We'll try to get to as many of them as we can. And without too much further ado, I would like to welcome Dr. John Berteau, Professor and Associate Provost for Faculty Affairs, for our opening remarks today. Thank you, John. Turning it over to you.
Sure. Thank you, Jennifer. Good afternoon, everyone. As Jennifer mentioned, I'm John Berteau, Associate Provost for Faculty Affairs. And it really is my great pleasure to welcome you to the 2020-2021 Distinguished Scholar Lecture Series. The Distinguished Scholar Teacher Award was established in 1978 to recognize tenured faculty members who are committed to and have demonstrated excellence in instruction and in their research efforts. The award is sponsored and administered by the Office of Faculty Affairs on behalf of Provost Marianne Rankin. Selected by DST recipients, over 200 faculty have been recognized for their outstanding scholarship and teaching since its inception. I'm very pleased and honored on behalf of Provost Rankin to recognize Dr. Derek Paley as one of our newest Distinguished Scholar teachers. As we will hear more shortly, Dr. Paley is widely recognized for his work in the area of dynamics and control, including cooperative control of autonomous vehicles, adaptive sampling with mobile networks, spatial modeling of biological groups, and bioinspired robotics. Among his many leadership and affiliate roles, he serves as director of the Maryland Robotics Center. He teaches introductory dynamics, advanced dynamics, aircraft flight dynamics and control, and nonlinear control. He's recognized for his engaging teaching style, passion in the classroom, and mentoring. Provost Rankin and I congratulate Dr. Paley on this much-deserved award and recognition. It's my pleasure now to introduce Dr. Norman Worley, who will formally introduce Dr. Paley.
Well, good afternoon and welcome to this outstanding lecture by Dr. Paley. Dr. Paley is the founding director of the Collective Dynamics and Control Laboratory in the department and is current director of the Maryland Robotics Center. Dr. Paley received his bachelor's from Yale University in applied physics and then went on to get his PhD in mechanical and aerospace engineering from Princeton University. He joined the department shortly thereafter, and he was awarded a National Science Foundation Career Award. And then a couple of years later, he was awarded the Presidential Early Career Award in Science and Engineering, which is the highest accolade given to early career scientists and engineers in the nation. Based on his research prowess, he's been promoted to Associate Fellow of the American Institute of Aeronautics and Astronautics, and is a senior member of the Institute of Electrical Engineers. He was also awarded the Engineer of the Year by the AAAA National Capital Section in recognition of his outstanding contributions to research in collective dynamics and control of aircraft and heterogeneous vehicle collectives. Although Dr. Paley is an outstanding researcher, he's also an outstanding teacher. And this award, the Distinguished Scholar Teacher Award, is meant to recognize both aspects of his professor activities. And but we already knew he was a great teacher. We appointed him to the Willis Young Junior Professor of Aerospace Education, so chair professorship, in 2012. And he's a co-author of an outstanding book on engineering dynamics. So please join me in welcoming Dr. Paley for his lecture on collective behavior in bioinspired autonomous robots.
Thank you, Dr. Worley and Dr. Berteau. It's an incredible honor to receive this award and be among this extraordinary cohort that will be presenting seminars throughout the year as part of the Distinguished Scholar Teacher Lecture Series. I'd like to also thank the committee, the selection committee, as well as all of the students, faculty, and staff whom I've had the privilege of interacting with. I'd like to point out that no faculty member can be successful without the support of a really excellent department chair. And Dr. Worley has been that chair for me in the most recent years. I was also very fortunate to have as my very first department chair someone who's now president of the university, President Pines. So I've been really blessed in that regard, and I give a lot of credit to my success to the kind of mentorship and support I've had from Dr. Worley, from Dr. Pines, and others, including my co-nominator, Dr. Reza Gotzi. So I just wanted to start by expressing gratitude for that. And one other note, I noticed in the list of prior recipients of the award, there's only been one other recipient in the Department of Aerospace Engineering, and that is one of my idols, John Anderson. And I have here a copy of John Anderson's book that I used when I was in college, Introduction to Flight. And so it's an incredible honor to receive the same award that Dr. Anderson did many years ago. So I'll be talking today about my research in collective behavior in bioinspired autonomous robots. When I arrived in 2007 at the University of Maryland, I founded the Collective Dynamics and Control Laboratory. And I've been very pleased and honored to advise numerous graduate students and PhD students and postdocs who've gone on to take faculty positions at a number of top universities across the country. And I list those here because indeed it's the proudest legacy of a faculty member to have their students go on to become faculty themselves. And so I want to acknowledge those students, too many to name here, but I will be referencing much of their work throughout today's presentation. I'd also like to draw your attention to the Maryland Robotics Center, which I direct. It's part of the Institute for Systems Research. The Robotics Center has over 40 faculty at the University of Maryland working in the area of robotics. And if, like me, you need to take a mental break during today's Zoom lecture, please check out our website or any of our social media sites listed there. I want to acknowledge all of the collaborators I've been fortunate enough to work with for my career, and much of their work is indistinguishable from my own work in the sense that we work together on problems. And so what I present today reflects not only what I've done with my students, but also with our collaborators, including those listed here. And indeed, at a research university, the basic knowledge could not be generated without support from external sponsors. And so I've been very fortunate to have support across a wide range of government agencies, as well as private foundations, supporting the work that I'll be presenting today. So what is collective behavior? Well, this clip shows some examples, and hopefully you can see the movie reasonably well through the Zoom interface. But collective behavior is what emerges in a group of individuals, sometimes fairly simple individuals, and it is best exemplified by biological systems. Here is my colleague Ian Cousin, perhaps the world's expert on collective behavior, talking about the wide range of organisms that exhibit this, ranging from birds to bats, and even in the underwater domain to schools of fish. And it's these beautiful, elegant patterns of motion that inspire me to study how we might be able to create engineered systems to replicate that behavior. To demonstrate the extent to which collective behavior is intrinsic to human society, I want to draw your attention to this list of words that are in the English language. These words describe the various collectives that appear in natural systems. Some of them are familiar to us, like a pack of dogs, but others are less familiar. And you can see, maybe pick out some of your favorites here. I want to draw your attention because at the University of Maryland, we are terrapins, and you may not have known that a group of turtles is called a bale or a nest, but it's the range of words and descriptions that exist in our language that demonstrate the ubiquity of this phenomenon in natural systems. But how do we go about modeling it? And so our story begins to some extent in the 80s when a computer graphics researcher named Craig Reynolds created a very simple program called BOIDS, B-O-I-D-S, to try to describe the behaviors that we see in natural systems. And this very simple computer program formed the basis for graphical animations that found their way into movies like The Lion King and Batman Returns. And what you see here are individual agents moving around in collective patterns. By obeying simple rules, they can avoid boundaries and align with their neighbors. You notice when the neighbor alignment is turned off, the movement gets much less coherent. Whereas if it's turned back on and other parameters of the model are changed, the rather elegant motion returns. And this is a hallmark of collective behavior, that very simple rules can produce very complex behavior at the level of the group. So flash forward to present day at the University of Maryland. Here are 3 quadrotor drone aircraft that are flying in our Fearless Flight Facility, an outdoor flight facility in College Park. And the purpose of today's talk is to tell you how we got from that basic computer graphics demonstration to the actual physical embodiment of collective behavior in robotic and aerial systems like these quadrotor drones. I'd like to point out that we also have a very unique resource at the University of Maryland, which is the Nutribuoyancy Research Facility. And it's here, and I apologize, this video seems to be a little bit jerky, but it's here that we also are developing an underwater vehicle test bed that I'll be telling you more about. So this all starts, as Dr. Berteau mentioned in the introduction, I teach dynamics and controls. And so the story today begins with dynamics. And so I hope to give you an understanding of what I mean by dynamics and its counterpart, controls. And together, dynamics and controls forms the foundation of my research, it forms the foundation of my teaching, and it forms the foundation of what we'll be presenting today as kind of a theme or motif throughout the talk. Because when coupled with sensing and estimation in the block diagram shown here, dynamics and control form the heart of what is called an automatic control system. I would say as nearly ubiquitous as collective behavior is the notion of an automatic control system. Even before self-driving cars, we had cruise control. And even before robotic systems, we had automated systems. And automatic controls is the foundation of that type of autonomy. And so I'll be walking you through how this theme and these elements, dynamics, control, sensing, and estimation, how they contribute to our research in collective behavior. So flashback almost 20 years ago, right out of college, I had the privilege to work for a small company called Bluefin Robotics, based in Cambridge, Massachusetts. And I fell in love with the technology of autonomous underwater vehicles. These small yellow submarines were capable of operating without a pilot, without any operator input, autonomously below the surface of the ocean. And when on the surface, they have the capability to collect GPS measurements, to transmit any data through a wireless connection to the operator. But when underneath the surface, they had to operate independently and do that using only their onboard software programming. It was at this point in my career that I knew what I wanted to work on. This image shows an example of the kind of data that an autonomous underwater vehicle, or AV, can collect. This is an image, but unlike the images we collect with our cell phones, which are based on light, this is an image based on sound. And the vehicle emits sound and records the reflected sound energy from obstacles or objects in the environment. So let me orient you. This is the right side of the image is the right side of the vehicle, and the left side of the image is the left side of the vehicle. The line in the middle of the image is actually directly underneath the vehicle. And you can see this acoustic image can actually form very precise, you can spot very precise objects in it, including the outline of this shipwreck on the right-hand side, and including what looks to be almost similar to a shadow to the right of it. But how does the vehicle collect these acoustic images? Well, let me try to describe it using this cartoon. It actually has to solve a very complex problem, and I'll remind you that there's no pilot or operator on board to control it. So the vehicle actually has to travel underwater, maintaining roughly a constant altitude above an ever-changing terrain, and to turn and rotate its propeller in such a way as to steer the vehicle, even in the presence of what might be variable water currents. And only by doing so very precisely and very consistently do those acoustic images reveal features of the seafloor. And so let's investigate how that problem is solved. And so let's return now to our theme, and let's talk a little bit about the dynamics. And so everybody gets exposed to Newtonian dynamics even as early as elementary school, and then again in high school, and then in freshman physics in college if you're in engineering, and then again in the class that I teach to my undergrads, some of whom may be on the Zoom today, which is called dynamics. And what we know about Newton and Newton's laws is that they apply to something called a particle or a point mass. And indeed, the influence of outside forces can affect the momentum, what we call the translational momentum of that particle. But underwater vehicles are not particles or point masses. There's something called a rigid body. And rigid body dynamics were derived by Euler a little time after Newton. And rigid body dynamics include not only translational, but also rotational momentum, because unlike a particle, a rigid body has an orientation in space. And its orientation changes under the influence of external moments. And so the relationship of the forces and moments and the translational and rotational momentum are described by Euler's laws. However, as we'll see later in the talk, we are going to study even more complex systems than those described by rigid bodies, and including flexible bodies. And for those, we often turn to energy methods, courtesy of Lagrange. And so these are the historical origins of the dynamic modeling that we use. But how do we describe these laws mathematically? We do so using the mathematical construct of a differential equation. So bear with me here. A differential equation is an equation involving a derivative. And if you remember from calculus or even pre-calculus, a derivative describes the rate of change of one quantity with respect to another quantity. And so here, the derivatives that we're representing on this slide is the rate of change of the quantity x with respect to time. Now, what is x? X is a variable. It might represent, for example, the position or orientation of the underwater vehicle. And this expression says that how the position and orientation of the underwater vehicle changes with respect to time is some function of the variable itself and this quantity u. And that brings us back to this block diagram, the arrow coming in from the left, because u represents the control input. We actually have the ability, for example, using the propeller of the underwater vehicle to change the dynamics. And so typically when we derive our control inputs and we design them, we imagine that our control input is in fact a function not of time, but rather of the state variable itself. How we control the vehicle depends on the current configuration of the vehicle. And so that's what this mathematical expression here means. And as a simple example, I'll present to you a linear control. Because when I was working on the bluefin submarines, that's pretty much all that we understood, is how to do linear, what we call proportional control, where this matrix K is a constant matrix that's multiplied by the state variables and used as the control input. And this minus sign here is so important, it shows up on our block diagram, and that refers to the fact that this diagram and this mathematical representation of the diagram is a description of what we call feedback control. And feedback control is an essential component of an automatic control system. So with that in mind, I decided that I needed to learn a lot more about dynamics and controls. And so I left Bluefin to study at the graduate level. And it was there that, along with my advisor, Professor Naomi Leonard, that I had the opportunity to work with a different type of underwater vehicle known as an underwater glider. Underwater gliders are similar to propeller-driven vehicles in that they have a GPS that can be used only when they're at the surface. But unlike the AUV I showed previously, there is no propeller. And in addition, they sport a pair of wings, which allows them to travel very elegantly through the water by changing an internal mechanism that controls their buoyancy. And specifically, underwater gliders change their buoyancy by taking on or expelling a very small quantity of seawater, about the size of a can of soda, actually. And by taking on and expelling a small amount of water using their buoyancy control system, it generates vertical velocity through the water column, which is converted to horizontal velocity using their wings. So the motion of an underwater glider is a little different than an AUV. They tend to poke their tails up when they're at the surface to communicate and to get GPS. And then when they descend, they take a very lazy glide angle down because they're heavier than water at this point. And at the bottom, the inflection point, they expel that extra 12 ounces of seawater and they become lighter than the surrounding water. And they ascend and they continue to do that before eventually traveling anywhere from 10 to 2,000 meters before surfacing again. And so this is the basic profile of an underwater glider that's used to collect measurements, not acoustic images, but rather hydrographic measurements to understand the properties of the ocean domain in which they're deployed. And so this chart that I adapted from a graphic has time on the horizontal axis and space on the vertical axis. And what's shown in this plot, if I draw your attention to these colored ellipses, are the various oceanographic phenomena that exist. And the dashed lines show how we might sample those processes using either AUVs, the propeller-driven vehicles, or gliders. And what you see here is that the space-time volume carved out by AUVs, while it's a little bit taller in the space domain, it doesn't carry the same width as gliders. And that's because gliders, due to their rather elegant propulsion system, can stay in the water much longer than AUVs. Their battery simply lasts longer. And as a result, they can capture these other processes that are invisible to AUVs because they don't stay in the water more than a day or two. Now, on the other hand, AUVs can travel faster, and that's what explains this slight benefit you see here. And to compensate for that, underwater gliders are often deployed in groups. They're deployed as a network of gliders so that at any instant in time, there is a whole fleet of gliders sampling this very same ocean process. And it was this type of deployment that I worked on for my PhD dissertation. And so along with my advisor, Professor Naomi Leonard, we developed the Glider Coordinated Control System, or GCCS, which is shown here graphically, controlling 10 gliders in the Monterey Bay Canyon off the coast of California. And so by coordinating the motion of multiple underwater vehicles over weeks and months, we were able to record and capture oceanographic processes that were taking place over large spatial and temporal scales. And so to understand how we built the Glider Coordinated Control System, I want to draw your attention to a very simple mathematical concept known as a graph. So each red circle on this slide represents what's called a node or vertex of the graph, and each line represents an edge between two nodes. And so we think of the gliders in the sampling network as, in fact, a graph. And if you number the nodes in the graph, as shown here, then you can use tools from linear algebra to describe a graph using matrices. And so the first matrix that you can form by inspection is what's called the degree matrix. And the degree matrix simply has on the diagonal the number of edges incident on a particular node. So node number 1 has 2 blue edges coming in, so there's a 2 in that spot of the diagonal, whereas node 4 only has 1 edge. The adjacency matrix, on the other hand, describes the blue edges. So node number 1 has edges connecting it to nodes 2 and 3, and those are represented by the 1s in the second and third column of the first row of the adjacency matrix. So by inspection, we can pass from a graphical representation of the graph to an algebraic representation. And by subtracting the adjacency matrix from the degree matrix, we form this very special and important matrix called the Laplacian matrix. And it's the Laplacian matrix that's going to allow us to control the fleet of gliders. So around circa 2010 or so, there was an emergence of a series of techniques for coordinated control known as consensus. And so consensus is a very, very simple algorithm. It's deceptively simple. All we have to do for consensus is to use the graph Laplacian in place of the proportional controller k that I showed before. So if x here represents the positions of the gliders in the network, then simply by using Laplacian feedback here, rather than proportional feedback, I can actually drive the vehicles to reach consensus, which in the case of a planar distribution would mean they rendezvous at a particular point. On the other hand, if the vehicles if we're thinking about the vehicle orientation rather than its position, then we have to think about consensus on a surface that's not necessarily flat. So drawn here is a circle, and you might imagine that the position of each dot on the circle represents the orientation of the velocity of that agent, maybe an underwater glider. And so velocity orientation is an angle. You could think about it as a number between 0 and 360 degrees, for example, but with the caveat that 0 and 360 are actually the same point on the circle. And so when we think of consensus on non-flat surfaces like the circle, we think of it in terms of what's called synchronization. And the algorithm for synchronization, although it uses an angle rather than a position, still involves using the graph Laplacian. So these ideas generalize very well, namely the ideas for control of network systems. And I'll just point out that synchronization here corresponds to the case when all of the agents are traveling in the same direction. Okay, so around this time, I arrived at the University of Maryland, one of two faculty I'll point out that was hired by President Pines, actually, when he was chair of aerospace engineering. So I share that very special bond with him. It's quite an honor, in fact, to have that connection. And my very first student, Cameron Peterson, worked on applying these consensus and synchronization algorithms to this fleet of autonomous unmanned aerial vehicles fielded by the Johns Hopkins Applied Physics Lab. And so Cami, shown here on the right, developed a coordinated control system to allow her to steer these vehicles into coordinated and synchronized patterns. And notably, the key extension of the prior work here was to accommodate the fact that the vehicles were operating in potentially very windy conditions. They're very lightweight vehicles, in fact, and so even a slight breeze was enough to deviate them from their planned trajectory. So how we modified the work was to allow the consensus and synchronization algorithms to work even in the presence of wind. And so once we had that framework, we decided to tackle an even more challenging problem. And that is, how might we use autonomous unmanned aerial vehicles to sample a weather system such as a hurricane. Shown here is a high altitude unmanned aerial system known as the Global Hawk. Global Hawks, while very effective at capturing remote sensing data, fly so high that they actually don't experience any of the wind of the hurricane. And it's similar, in fact, to the type of data that you could collect from a satellite. And it's through high altitude and remote sensing data that forecasters can predict the trajectory of hurricanes. And shown here in this probability plot that we are all familiar with, probably all too familiar with, I should say. These plots are generated by assimilating high altitude observations into computer models that forecast where the hurricane can go. But what motivated us in our work was the fact that while predictions of where the hurricane might make landfall have improved over the decades, what has not improved is the predictions of how strong or intense the storm will be. And the intensification or rapid intensification of a hurricane occurs as a result of energy that's transferred from very warm ocean waters to the atmosphere. And to capture that energy transfer, you actually have to fly and sense the hurricane at low altitudes near the air-sea interface. And so along with collaborators at the University of Miami and the National Hurricane Center, we worked to understand how we might use the Aerosonde unmanned aerial system shown here to do just that, to sample hurricanes in situ at low altitudes to collect data that would be critical to predicting the intensity of the hurricane upon landfall. And so we were able to develop a modeling system, but in order to explain that, we have to turn our attention to the sensing block in our automatic control system. And so the first line here is a restatement of our dynamics, which includes the control input on the right-hand side. The second line is a description of a possibly nonlinear relationship between the states of our system and the outputs y. These describe the measurements. And it was with my student Levi DeVries that we investigated how we might use the concept of observability to select the measurements that would be most informative. And so using a concept known as the Observability Gramian, which is a matrix whose kjth entry is given here by this integral, qualitatively what the Observability Gramian describes is the sensitivity of the outputs to perturbations of the states or parameters of the system about a nominal value. And so we sought to select sampling trajectories that were maximally sensitive, that rendered the system maximally observable. And so to give you an example of that, consider the eye wall of a hurricane to be a perfect circle. And that's the dashed line shown here in a couple places on the plot on the left. Now imagine that we're going to fly the Aerosonde aircraft also in a circle, but we have some choices about the parameters here. So we partition the parameter space into, roughly speaking, 4 different parameter sets. Parameter set number 1 is when the Aerosonde aircraft flies a circular trajectory that's contained entirely by the eye wall of the hurricane. Whereas parameter set 2 is when the Aerosonde flies a trajectory that intersects the eye wall. And you can see the other parameter sets shown here when it stays outside and when it stays outside and doesn't enclose the hurricane at all. On the right-hand side, the color represents the unobservability index. Smaller here is better, right? And this is formed by taking the reciprocal, the smallest singular value of the observability Gramian. And the main point here is that there is a trajectory that is optimally observable. Namely, this very small circular trajectory that rapidly crisscrosses the eye wall of the hurricane is the minimum of this plot. And so that's an example of how we could use observability theory to not only characterize the sensor trajectories, but actually select among candidates sensor trajectories the ones that are the most informative. Okay, but hurricanes are just one vortex, and this NASA animation shows that vortices are actually very, very ubiquitous in both the atmosphere and the ocean. You can see here how the ocean currents respond to interactions with each other and interactions with the land surface to create beautiful, persistent patterns of movement and circulation in the ocean. And so the question is, how might we develop a strategy to better understand these types of patterns? And so I'll point out that, as a matter of fact, there exists a robotic network of underwater vehicles known as the Argos fleet that at the moment, or as of last week, October 14th, nearly 4,000 robotic floats are deployed. These are floats that are, you can think of just like an underwater glider without wings, basically. So they have a buoyancy control system. They go up and down. When they reach the surface, they can connect to a GPS satellite. But when they're underwater, their only means of actuation is by changing their buoyancy, namely by descending down through the water column. But nonetheless, by deploying many thousands of these robotic profiling floats, scientists can begin to understand those circulating ocean patterns that I just showed. But we wanted to ask the question, what if we had a control input? What if we could steer these platforms? Where would we send them? And so we developed a system, along my students and I and our collaborators developed a system we think of as adaptive sampling. And the adaptive sampling system has on the right-hand side our familiar block diagram that integrates dynamics, control, sensing, and estimation. But each of those is shown here for one of n possible vehicles in our adaptive sampling network. And it's together by incorporating outer loop distributed control and estimation, along with optimization and task allocation, that we can solve this problem. And I only have time to give you one quick example of this, but it comes from a system with 2 vortices. So along with my student Frank Lugor, we studied the 2 vortex system. So imagine these are the Argo profiling floats here on the left. The 2 vortex system shown here with the red dots exhibits a circulation pattern as shown. And what Frank detected is that there are certain boundaries in the flow field that the profiling floats, because they're just drifting, would never cross. And here you see the same animation, but in a frame that's rotating with the vortices. And you can perhaps see the patterns of movement in each one of these regions. And what Frank showed is that actually by steering a sampling platform along these boundaries, the black curves, then you can maximize the observability of this 2 vortex system. And so here's an example of that with a single vehicle. The single vehicle travels along this boundary, then switches to another boundary before wrapping itself around this boundary several times before switching again. And in doing so, it optimizes its ability to estimate the states of the system, and I've just shown 2 of the state estimates here. The plot in the middle is a description of the strength of the vortex on the left. And the color represents the probability. So the y-axis here is the strength of the vortex, and the horizontal axis is time. The color shows how confident we are in our estimate of that parameter. The white line is the ground truth. And you see that over time, by collecting measurements in these optimal ways, namely by transitioning between these boundaries, we're actually able to estimate, as shown by the red color here, at a very high probability. And the same goes for the position. The ground truth, again, shown in white, and the estimate shown in color. And you see how the estimate converges from rather diffuse, mostly blue color, to the reddish color shown on the right. And the way that the estimate converges is using a very powerful tool from estimation known as Bayes' theorem. So I'll take a moment to explain this because I think it's a very elegant and powerful theorem that underlies most of what we do in the estimation block. Now, imagine that you're playing darts, but instead of one dartboard, there's two overlapping dartboards. And now suppose you throw the dart and it lands in the yellow dartboard. So Bayes' theorem allows you to understand what is the probability that, given that the dart landed in the yellow dartboard, what is the probability that it actually landed in the orange part of the yellow dartboard, namely the part of the yellow dartboard that overlaps with the red dartboard. And this type of question is known as a conditional probability, denoted by this vertical line here. So if P is the probability, the way we read this statement is we say, what is the probability that A occurs given that B has already occurred? And we can ask the same question in reverse, namely, what is the probability that B occurs given that A has occurred? And the relationship between those two conditional probabilities and the probabilities of events A and B occurring at all, namely, did your dart even hit the dartboard, is described by Bayes' theorem. And Bayes' theorem, as I said, is the heart of the estimation that Frank and my other students use in order to take sensor measurements and form an estimate of the system in question. So turning to increasingly complicated circulation patterns, we started to investigate this particular vortex structure, which not only exists at ocean basin scales, but also exists at much smaller scales too, including the scales of an individual fish. So biological systems like fish have evolved a very intricate sensory organ on the surface of their skin. And this organ is known as the lateral line. And it's known as the lateral line because it predominantly exists along the side of the fish body. But there are two types of sensor nodes in the lateral line. There's a superficial node and a canal node. And these respectively measure flow, shear flow velocity, or in the case of a canal neuromus, they can actually measure pressure gradients. And by using the lateral line system, fish in flow can actually perceive information about the flow, including the presence of stimulus. And as we'll see later, they also shed their own signature in the flow that might be perceived by other fish. And so here's an example of a fish exhibiting what's called a Kármán gating behavior. You can't see in this animation, but there are vortices being shed from an upstream obstacle in the manner that I showed just a few slides ago. So we asked the question, how might we make a robotic fish that could exhibit that Kármán gating behavior? And so circling back to our dynamics, we had to describe the fluid dynamics in the vicinity of this smooth, streamlined body. And inspired by work by Dr. John Anderson and others, we used a very simple model of the fluid dynamics called potential flow. And potential flow allows us to model, in fact, the airflow over the cross-section of an airplane wing. And so it wasn't very difficult to take that cross-section of an airplane wing, turn it on its side, and call it an underwater vehicle. Potential flow involves a derivative, but not with respect to time, a derivative with respect to space. And the potential here, U, when you differentiate with respect to space, you can actually compute the horizontal and vertical components of the flow velocity, U and V. And when you take the magnitude of the flow velocity, you get the flow speed, which is shown here on the left in terms of the color, red being faster and blue being slower. And so the way to understand the interaction between the potential flow model and the fish itself is using Bernoulli's principle. Bernoulli's principle says that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure. This is a fundamental principle that's important for the lift that aircraft generate, for example. It's also important in the context of underwater sensing, because by endowing our robot with pressure sensors shown here in white, and comparing the pressure between two sensors, we actually get an estimate of the difference in the velocity of the flow at the location of those sensors. And this relationship relating pressure differences to velocity differences is the mathematical representation of Bernoulli's principle. So armed with Bernoulli's principle and some robotic apparatus, my graduate student, Brian Free, developed the robot Kármán gating behavior. So what you see here is a flapper on the left generating vortices and a robotic fish on the right. It's not fully immersed in the water. It's in fact suspended over the water using these frictionless air bearings, but by turning back and forth in the water, it can generate lift that moves it from side to side. And the way that it controls its movement is using the information solely collected from 4 onboard pressure sensors. And it's those pressure sensors on board that allow it to perceive and estimate, using a Bayesian estimation scheme, the oncoming vortices, which hopefully you can see that it's successfully slaloming around. So this was our first foray into the Kármán gating behavior. Okay, but how do real fish behave? And how do fish interact with one another? So this is a little bit of a short video, so I'm going to loop it. So along with my graduate student Amanda Ciccoli, we started to investigate fish behavior. And the tracking here was superimposed by another student of mine, Sacha Boutal. And so this redfish that seems to be so passive and non-reactive has actually been treated with what you could think of as temporary contact lenses or frosted lenses. We basically put glue over the fish's eyes because what we want to understand is how the fish might respond to the behavior of its neighbors when it can only sense its neighbors using its lateral line. And so the other fish are actually startled by an external predator stimulus. And so Amanda was motivated by experiments from the 70s where Russian scientists startled fish using this propeller shape, and they tracked the evolution of the boundary between startled and non-startled fish. And what they showed is that by using interactions between the fish, they can transmit information through the school faster than any individual fish can swim. And you see by the last frame here on the right, all of the fish are fleeing this rather scary propeller shape, even though the majority of the fish have not perceived it directly. They're only responding to the cues of their neighbors. And so Amanda developed this state transition model where fish that are unstartled are, well, susceptible to becoming startled, again, either by external sources or sources internal to the school. From the startled state, the startle itself might wear off after a little while, in which case they go to the recovered state. And this model actually captured really well the behavior that we observed in our studies of fish. What we stumbled upon, actually, is that this is a manifestation of a classical epidemiology model known as the SIR model. And in fact, we are now all too familiar with the SIR model because it's the curve that we are currently trying to flatten. If you replace startled with infected, this is in fact a predominant model used to study COVID-19. But at that time, there was a different disease that I became interested in, and that is the disease of malaria. We worked with National Institute of Allergies and Infectious Diseases to study swarms of malarial mosquitoes. I don't imagine you can see them very well, and that's kind of the point. They're kind of hard to see. And so my student Sacha Boutal, after developing the tracking system for fish, developed a stereo camera rig with 2 cameras here and worked with researchers at an NIAID outpost in Mali, Africa, to film swarms of mosquitoes and to take those rather grainy images and convert them to three-dimensional tracks of the mosquitoes in flight, and doing this simultaneously in swarms of up to 50 individuals. You can see how by taking two simultaneous images, you can not only record their two-dimensional position, but also their three-dimensional position. And what was incredibly important to the medical entomologists that we worked with were the mating events. And so it is these mating events that Satya was able to recover for a number of different swarms and convert them into very beautiful representations, three-dimensional representations as shown here, as the solitary female shown in red loops into and out of the swarm before coupling with an individual male and falling to the ground. And these data were such a valuable resource that they're still in use today. So what is the model that we can extract from the mosquitoes? Well, it turns out a very mechanistic model suffices. In particular, if you imagine that the mosquitoes are coupled invisibly by a very conventional spring, like a slinky, for example. The male mosquito's behavior follows that spring-like motion, which for a simple spring can be represented exactly by the same linear proportional control law that we showed before. Furthermore, the interaction between the males in blue and the female in red, you could think of as a damped spring, because in addition to the proportional control, there's a term here, minus bx dot, that's proportional to the rate of change of the position of the particles, and in particular, the rate of change of the relative position. And so this term is like in a car, the damper, the shock absorber that prevents the car from bouncing too much when you hit a pothole. So armed with that model, my student Daigo Shishika was able to build a swarm of quad-rotor drones. These are operated indoors with the help of motion capture cameras, and were very successful at demonstrating the types of behaviors that we observed in the mosquitoes, plus some other behaviors that we added to it, like that circling behavior that was a very simple extension of the model. And moreover, we were able to simulate the intrusion of an individual female. And so here you see the tip of the wand that Daigo's waving. It's a little hard to see on the right, but you might be able to see it on the left. It's the red dot on the upper left side of the screen. And as the individual quadrotors perceive the intruder, they chase it. And so this was our beginning implementation of our quadrotor swarm, which eventually turned into the outdoor swarm that I showed at the very beginning of the talk. Now, at this time, I was able to take advantage of one of the benefits of being a scholar teacher, and that is to take a sabbatical. And so I spent my sabbatical at the Laboratory for Autonomous Systems Research at the Naval Research Laboratory, because they had many more quadrotors and many more cameras than we did, and had a wonderful space to test them in. But it was when I was at NRL that I happened to see on a colleague's desk the very first issue, volume 1, number 1, of this new journal called Soft Robotics. And this very simple image showing an elephant trunk and a robotic analog of an elephant trunk just captured my imagination. It was the first time I really thought about robots that were soft, and really thought deeply about robots that were inspired by natural systems. And being at the Navy, Naval Research Lab, I kind of started to think about what would be a useful biological inspiration for the Navy and for maritime robots. And I came to conclude that the starfish, or sea star, might just be that. And so this is Cornelius. This is a chocolate chip starfish that we bought to study. And you see Cornelius moving to eat the jumbo shrimp that he very much enjoyed. And you see the remarkable behavior of this starfish organism, which does not have a central nervous system. It's a completely distributed system, which caught my imagination, not just between the 5 arms, but between the hundreds of small feet that protrude from the underside of those arms. And it was this type of distributed, decentralized behavior that motivated me to study a soft robotic starfish. So along with my postdoc, Will Scott, we started to develop robotic analogs of the starfish and modeled how we might control the locomotion gait of these multi-legged robots. And so along with our collaborators at Harvard and Carnegie Mellon, we started to research this. And in order to understand how we came about the model for that starfish, we have to revert to Kirchoff's rod theory. And I'll try to explain this very quickly. It's a complex theory, but I think you can get the gist of it. Unlike our rigid body models, this requires us to invoke the concept of energy. So being an elastic rod, the energy that this rod contains at any given time is a combination of the bending energy, the stretching energy, and the twisting energy. Those are the three flavors of energy that an elastic rod can possess. And those, again, with regard to stretching, can be understood as simple springs aligned with the longitudinal axis of the rod. And indeed, the force that arises due to those energies is once again a derivative with respect to space. And indeed, it's the gradient of the elastic energy that yields the forces that the rod produces. Like in the case of stretching here, this is just like, you see the resemblance to our simple spring model, where here I've introduced the rest length of the spring. So the displacement from the rest length of the spring is in fact proportional to the force that's exerted. So what about the control? How did we get the starfish robot to actually walk? Well, the control input here comes in as the rate of change of the intrinsic parameter of the system. And in the case of the stretching energy, it comes in as the change in the length of the rod. So this also applies to the intrinsic bending and twisting of the rod as well. It's a very straightforward model, and we were successful enough to get a back cover of the Advanced Intelligence Systems Journal. And here's the robotic analog of the starfish that we were able to build and demonstrate walking. So this also works for caterpillars. So along with our collaborators at Carnegie Mellon, I'll just show that one more time. It's a quick video. They built a robotic caterpillar, and we were able to model it and study its locomotion gaits using the rod theory that we had developed. So I'll turn now lastly back to fish, because this is kind of where we started. And I guess it goes without saying that this is also a soft robot, but its operating principles are a little bit different. So here's a top view of our robotic fish swimming. Its body is made out of molded rubber, but it contains an internal rotor that rotates back and forth in order to generate the swimming motion. So the question is, how did we come up with the control law for that internal motor? It comes down to a very simple system that my juniors this fall know all too well, which is that of a simple pendulum. And the dynamics of a simple pendulum are given here. They're second order dynamics, and they describe how the angle of the pendulum changes over time according to its initial conditions. One of the things about the simple pendulum, however, in the presence of gravity, is that the amplitude of the oscillations depends on the amplitude of the initial condition. If you start the pendulum from the down equilibrium, it's not going to swing. And that's not a property that we wanted with our fish. So with our fish, we were inspired by the pendulum, but we created an oscillating control. And the way that we created an oscillating control is we emulated the dynamics of a simple pendulum, but we added two additional terms. The first term here looks a lot like the damping term that we saw with the mosquitoes, but there's one key difference, and that is that this is no longer a negative sign. So this is actually the opposite kind of damping. This would not slow the tail beat down. this would actually speed it up. So this allows the fish to keep flapping, but it keeps flapping at an amplitude prescribed by this nonlinear damping term. And the control gains K1 and K2, along with the natural frequency omega naught, allow us to tune not only the amplitude, but also the frequency of our fish tail. And so you can see here some of the fish on the deck flapping their tail, and once they're in the water, their tail beats, again, due to the rotation of the internal motor, according to that feedback control law that regulates the amplitude and frequency of the flapping. Okay, so this work is ongoing with my graduate student, Anthony Thompson. I'll just show, conclude here. So here's the behavior of the oscillating control. It creates what's called a limit cycle, which is a rather beautiful structure in dynamical systems theory. And the corresponding motion from the top view of the fish, you see them actually achieving synchronization using the algorithm that we discussed earlier. However, fish don't tend to flap their tail continuously. This is not a behavior that fish do for energy reasons. And so with our collaborators at UC Irvine, we're investigating what's called a burst and coast model. So the burst phase is when they flap their tail, and that of course incorporates control and dynamics. The coast phase is when their tail beats stop, and when we believe they perceive the fluid wake signatures of the other fish. So by alternating between the burst phase and the coast phase, namely alternating between control and estimation, we think there's a really interesting trade-off there that the fish are doing inherently and that we would like to replicate with our robotic fish. And so these and other challenges, including how humans might interact with swarms of these and other robots, is the subject of ongoing work. And so with that, I will conclude. Thank you for your attention, and I'm more than happy to take any questions.
Well, thank you very much, Derek, for a really interesting lecture. If there are any questions, please feel free to use the Q&A tool at the bottom of your Zoom screen to pose a question. So we have a question from Ben Schneiderman. Jennifer, can we get Ben to ask his question?
Hi, yes. I think I'm unmuted. I thank you for an interesting talk, but I wanted to hear more about the swarming behavior and the examples of how swarming behavior in robots would be useful.
Absolutely. Thank you for that question. So there's sort of two parts to the question. The first is, or two parts to our research. The first is how do we enable the swarm? But as you point out, the swarm for swarm's sake alone is not really the goal. The goal is what are the applications? And so that kind of gets back to the early part of the talk where I tried to motivate it in the underwater domain. But basically, we think of each agent in the swarm as a sensor platform and a mobile sensor platform. And so the utility of the swarm as a distributed sensor network comes when the processes that you're trying to observe vary over space and time in such a way that individual solitary or static sensors would not be able to collect sufficient information to really describe that process. And so the oceanographic and atmospheric processes fall into this category where you really need a mobile sensor network, or a swarm as you call it, to sense it. And there are other applications as well. For example, with the quadrotor swarm, one of the applications we're working on is cooperative searching and mapping. For example, for search and rescue.
So wouldn't an array of robots simply do the job in an orderly way? I'm not sure why the swarming notions are needed. Intel shows some very sweet examples of swarming robots to create lights in the sky that draw different patterns, but I'm still struggling to find the meaningful applications of a swarm rather than an array of mobile robots.
Yeah, I think what you're getting at is some of the differences in terminology. So generally, this all falls into kind of what we call multi-vehicle control. And the array that you referred to might be a particular formation. By swarm, it sounds like you're using that as more of a biologically inspired, maybe a randomized component. So they all kind of fall into the same category of multi-vehicle controls. And the terminology is not exactly consistent. This term swarm kind of reminds me of the term drone. It's not really the best term, but it's the one that has caught on and has captured people's imagination. And so we kind of use that word swarm to represent a broader category of behaviors than simply the ones that might include some random motion.
Thank you. I mean, I think there's a reasonable case there, but you know, arrays in 2D or 3D would accomplish the aerial or underwater notions. But so I'm just concerned about the overreach of the bioinspired model. Thank you, but very interesting talk.
We have another question from DPL.
Yep, this is Dan Lathrop. Nice talk, Derek. So actually, your talk made me think about the starlings, the birds that go in large flocks and murmurations. And can your models be used to model their motions? And just a related question, would reinforcement learning models in machine learning be useful in these settings?
Yeah, so those are really great questions. So with regard to starlings, so one of the early data sets that was used to understand collective motion in biological systems came from a group of physicists in Italy who studied starling murmurations. So there were some very consistent patterns of starlings roosting, you know, around twilight above, I think, the train station in Rome. That's so predictable, in fact, that they were able to set up cameras similar to the stereo camera rig we used to track the mosquitoes and record the 3D positions of the birds in the flock. And what they learned from that is that it seems that starlings interact with other birds regardless of how far away they are, but only up to about 6 neighbors, regardless of the density of the flock. And so that was a very interesting distinction between some of the early models of swarming that were distance-based. This was distance in another sense, distance on the graph, actually. And with regard to your second question, absolutely. One of the ways that we're using machine learning, and it reminds me of your talk a few years back, Dan, is for time series prediction. And so some of the complex behaviors that we observe in multi-agent systems, whether they're animal groups or even human groups, because we're using some of this to model mobility patterns in transportation systems, is that there really are no simple dynamical equations that can represent these complex systems. And so instead, we take an approach driven by data, driven by observations. And by collecting enough observations of a dynamical system and using a machine learning technique, such as those that you work with, in fact, we're actually able to come up with a model that's determined empirically, but it has very good predictive power nonetheless.
Oh, thanks, Derek, and congrats on the DST, and let's chat sometime.
Happy to do it.
Okay, we have one question from Sarah Over. Are you available, Sarah?
Yep. Can you hear me?
Yes.
Okay. Yeah, it sounded like you were already starting to touch on this, but I was curious about how much you've tried to apply these types of models to human behavior, whether it's traffic or pedestrians. Like, it made me think of the students walking across campus. Like, if there's a sudden noise in a certain part of campus, the students might move one direction or another.
Absolutely, yeah. So there's a lot of research about pedestrian movement and crowds, and a lot of it is based on agent-based models. In fact, there's what's called a social force model for pedestrian movement. We are working with it actually in the context of what's called micromobility. And so we're very interested in thinking about what we see on campus. Before the pandemic, we saw a lot of scooters and bikes. And so that scooters and bikes represent a mode of transportation that's meant to be more sustainable than cars and buses, but has their own problems and challenges with regulations and safety. And so we're using some of these models to understand what is the proper guidance for use of scooters and bikes in crowded pedestrian settings. What are the pros and cons, and how might we take advantage of some of the pros without some of the public safety concerns?
Yeah, thank you. That's great talk. And as a bicycle commuter, I'll be looking forward to that research.
Thank you.
We have a question from Stephanie Patillo. I hope I said your name correctly.
Almost. Can you hear me?
Yes.
Hi, Stephanie Patillo. Hi, Derek. It's nice to see a talk from you again. So it seems like most of the work you've been doing is on like reactive based on individuals. And I was wondering if you had to deal with data fusion from data coming from your swarm to do more sort of decentralized behavior control, or if you've just been working on based on like the feedback loops on each individual.
Yeah, that's a really important part of the research, the extent to which the estimation algorithms are distributed or centralized. And there are some really important questions there as well. So the basic data fusion algorithms that we use, because they rely on Bayes' theorem at the core, are possible to implement in a distributed fashion. And so that does allow us not only to integrate information from multiple agents, but to integrate information from multiple types of sensors. So just using the fish as an example, in addition to their lateral line, fish have vision, they have eyes. And so we're modeling how we can incorporate different sources of information into one estimate, a single estimate of, for example, the position and orientation of their neighbor, let's say. But with regard to the collective behavior, that is one of the hallmarks of distributed sensor networks, is that even if the information that each individual agent is collecting is perturbed by noise, the spatial integration over the collection of agents can resolve the signal despite the presence of that noise.
Have you done this using a external mission planner at all, or central leader versus distributed control like you're talking about?
Yeah, I mean, it really varies on the application.
Okay.
And it varies according to the level of communication that's available. So oftentimes we design distributed algorithms, but then when we go to implement them, if there is sufficient communication, we might implement them in a centralized manner. So that's one of the ongoing areas for us with our experimental test beds, is to sort of intentionally cut the communication channels, eliminate the ground station, for example, so that the agents are working more peer-to-peer. At the heart of it, the algorithms are designed for that, but our experiments are kind of lagging behind.
Cool, thank you.
Well, you've had a number of great questions and a great lecture, so it's probably time to start thinking about wrapping this up. So thanks again, Derek, for, first of all, being an outstanding faculty member, scholar, and teacher, and for also delivering this wonderful lecture to everybody. And I want to thank the audience for coming, and also thank John Berteau for his role in making sure this program goes forward, and the Distinguished Scholar Teacher Award. It's a great award, and we've had the opportunity this year for a number of lectures, so keep your eyes peeled for additional announcements. So again, Dr. Paley, thank you very much.
Thank you. And thanks for coming.
Great. Thank you, everybody. Have a wonderful afternoon.